Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. Now, in this second video lecture of week 12 for the course Differential Equations, we are going to learn about the solution of higher order non-homogeneous linear differential equation, case number 3. Dear students, note that case number 1, case number 2 and case number 3 is related to the particular solution of non-homogeneous higher order linear differential equation. I have already told you in the previous video lectures that when the function in the non-homogeneous differential equation f of x, actually f of x is the non-zero function. F of x is a function of x which lies in the right hand side of the higher order non-homogeneous linear differential equation. So when the function f of x is in the form of exponential function, then how we can find the particular solution? We have discussed this case number 1 in the previous video lecture of week 11. And when the function f of x in the form of trigonometric function like sine ax and cos ax, sine ax or cos ax. So we have already also discussed this case in the first video lecture of week 12. Now in this second video lecture, which is the continuation of my previous first video lecture of week 12, in this second lecture we are going to learn case number 3, when the function f of x in the form of polynomial form. So then how we can find the particular solution?
So this is case number 3. Suppose we have a function f of x in the form of x power m. X power m is a polynomial of degree m, non-negative integer. Then how to find the particular solution for the non-homogeneous differential equation? Then the particular integral is equal to 1 over differential operator into x power m. Now this is f of d is in the differential operator. So how to apply 1 over f of d on this polynomial? Take common the lowest degree term from this differential operator. Here you see lowest degree term in this differential operator polynomial into 1 plus minus pi of d into x power m. Now the lowest degree term, 1 over the lowest degree term, shift this expression 1 plus minus pi of d, pi is the function of d, to the numerator. We obtain 1 plus minus pi of d power minus 1. Now this is the binomial theorem. Expand this binomial theorem for the particular integral, we can obtain the particular solution of the given non-homogeneous higher order linear differential equation. So how to find the particular solution when the non-homogeneous equation in the right hand side has the function in the form of a polynomial? You see over here an example. Suppose this is third order linear differential equation. Y triple dash minus y double dash minus 6y dash is equal to x square plus 1. So this is the polynomial, and if this is called f of x function at the right hand side of non-homogeneous differential equation. Now this is non-homogeneous linear differential equation of order 3. So there will be two solutions. One is the particular solution and other is the complementary solution. One will be the complementary solution and other will be the particular solution. For the complementary solution, consider the homogeneous case for this non-homogeneous equation. The homogeneous case is a y triple dash minus y double dash minus 6y dash is equal to 0. Now the complementary solution of this homogeneous part is depend on the roots of the auxiliary equation, and depend on the nature of the roots of the auxiliary equation. So the auxiliary equation for this homogeneous equation is m cube minus m square minus 6m is equal to 0. Now factorize this polynomial. M into m square minus m minus 6 is equal to 0. And now this implies that m is equal to 0 and m square minus m minus 6 equal to 0. So factorization of m square minus m minus 6 by sum and product, we obtain m square minus 3m plus 2m minus 6 is equal to 0. And now taking common m from these two terms, m into m minus 3, and taking common 2 from these two terms, plus 2 into m minus 3 is equal to 0. And this expressions can be written as m minus 3 into m plus 2 is equal to 0. Now m minus 3 is equal to 0 and m plus 2 is equal to 0 mean m is equal to 3 and m is equal to minus 2. So there are two real and unequal roots for the auxiliary equation. So the complementary solution for the homogeneous part will be equal to c1 e power m1x plus c2 e power m2x. And now c1 m1 is 3 and m2 is minus 2. So the complementary solution c1 is equal to e power c1 into e power 3x plus c2 e power minus 2x. This is the complementary solution, and we have already discussed in the previous video lectures. Now the particular solution, this is very important. The particular, how to find the particular solution when there is a polynomial function at the right hand side of the non-homogeneous linear differential equation. Then how to find the particular solution? So this is the given differential operator d cube minus d square minus 6d, and 1 over d cube minus d square minus 6d treated as a integration. So 1 over d cube minus d square minus 6d into x plus 1. To apply this integral operator 1 over d cube minus d square minus 6d on this polynomial. So take the lowest degree term. This is actually the lowest degree term. The degree of this term is 3, the degree of this term is 2, and the degree of this term is 1. So this is the lowest degree term. Take common the lowest degree term minus 6d. We can write 1 plus d by 6 minus d square by 6. If we multiply minus 6d again to this terms, we obtain d cube minus 6d, d cube minus d square minus 6d. Minus 6d multiplied 1 minus 6d, and minus 6d multiplied d by 6. 6 and 6 cancelled, we obtain minus d square, and minus 6d multiplied d square by 6. Minus 6 and 6 cancelled, and d square is equal to d cube. So d cube minus d square minus 6d can be written as minus 6d into 1 plus d by 6 minus d square by 6. Now to obtain the binomial expansion, you see over here 1 over minus 6d into 1 plus d by 6 minus d square by 6 power minus 1. Dear students, actually 1 is the first term and d by 6 minus d square by 6 is the second term. So 1 is the first term and x mean d by 6 minus d square by 6 is the second term of the binomial theorem. So for the binomial expansion, this differential expansion can be written as you see over here in the previous slide. In the previous slide, minus 6d into 1 plus d by 6 minus d square by 6. So 1 is the first term and d by 6 minus d square by 6 is the second term. So to show the first term and second term, you see over here, this is the first term and d square by 6 minus d square by 6 is the second term. So the binomial expansion, the binomial theorem, when the power n is negative or rational, then 1 plus x power n can be written as 1 plus nx, multiply this n to this second term, 1 plus nx divided by 1 factorial plus n into n minus 1 into x square divided by 2 factorial plus n into n minus 1 into n minus 2 x cube divided by 3 factorial and so on. So this is the binomial expansion when this power n is negative or rational. So now we have a negative power minus 1. So this is binomial expansion. For the binomial expansion, 1 is at it is, and now n is minus 1 and x represent this second term. So minus this is minus 1. So this is actually minus 1 is actually n represent n. So nx. So minus 1 into x. This is the this whole term represent the x term. Now plus n into n minus 1. Minus 1 into minus 1 minus 1 minus 2 minus 2 and minus 1 plus 2 and 2 factorial cancel. So you see over here, no, this is plus. So x square, this is the x term, d by 6 minus d square by 6 whole square, and so on into this polynomial. Now since we have polynomial of degree 2, so neglecting the d cube, actually d square means second derivative for this polynomial. So the third derivative for this polynomial will be 0. So we don't need third derivative and higher power of derivative. So neglecting the d cube and higher power, we obtain minus 1 divided by minus 6d into 1 minus 6d minus plus d square by 6 plus d square by 36. This is actually a square plus b square. A square mean d square by 36 and b square mean d power 4, but we don't need d power 4. And minus 2ab. In the a term we have obtained d, and in the b term we obtained d square. So d into d square d cube, but we don't need d cube and higher power. So we can write only just the a square term, d square by 36 into this polynomial. Now minus 1 over 6d into 1 minus d by 6 plus, taking the LCM of these two terms, we obtain 7d square by 36 into x square plus 1. Now this d means first order derivative for this polynomial, and d square means second order derivative for this polynomial. So applying first derivative or second derivative for x square plus 1, you see over here we obtain the particular solution is equal to 1 over minus 6d into 1 minus d by 6 plus 7d square by 36 into x square plus 1. Now x square plus 1 multiplied with 1, we obtain x square plus 1, and d mean the derivative of this term 2x, and the derivative of 1 is 0. So minus 1 over 6 into 2x, and 2x is the first derivative. So the second derivative for this will be 2, 7 by 36 into 2. Now x square, this is actually 1 over d, and 1 over d mean integration of x square plus 1 minus 2 3 the 6 x by 3 plus 2 18 the 36, so 7 by 18. So the integration of this with respect to x. Now integration of x square is x cube by 3, and the integration of 1 is x, and the integration of x is x square by 2, and the integration of 1 again is x. Now this is the particular solution. So the complete general solution is equal to complementary solution plus particular solution. This is the complementary solution, c1 e power 3x plus c2 e power minus 2x into complementary solution plus particular solution. Now this is the particular solution, 1 over minus 6d into x cube plus 3 plus x minus 1 over 3 x square by 2 plus 7 by 18 into x. Now another example, you see over here d cube plus 2d square plus d into y, which is equal to e power 2x plus x square plus x. Now we have case number 1 and case number 3 for the particular solution. So this is the non-homogeneous, third order non-homogeneous linear differential equation. So we have two solutions for this differential equation. One is the complementary and other is the particular solution. So as a whole, general solution will be equal to complementary solution plus particular solution. So first of all, find the complementary solution for this third order non-homogeneous linear differential equation. For the complementary solution, take the homogeneous part, d cube plus 2d square plus d into y is equal to 0. Now this homogeneous equation have two solutions. Y is equal to 0 will be the trivial solution, and we need non-trivial solution. For the non-trivial solution, we take the auxiliary equation m cube plus 2m square plus m is equal to 0. So taking common m, we obtain m into m square plus 2m plus 1 into equal to 0. This is the auxiliary equation for this homogeneous part. Now m is equal to 0 and m square plus 2m plus 1 is equal to 0. So m square plus 2m plus 1 mean m square plus 1 whole square, and m square plus 1 whole square mean m plus 1 is equal to 0 and m plus 1 is equal to 0. So we have two repeated real roots, m is equal to minus 1 and minus 1. In this case, we have one unequal real roots and we have two repeated real roots. So the complementary solution, there will be two cases. Case when roots are real and different. In case number 2, when roots are real and repeated. You see over here, this is real and unequal situation, c1 e power m1x, and this is real and repeated case, c2 plus c3x into e power m3x. m3 actually the m2 and m3 are equal, so we consider, just suppose this is m3. Now the repeated root is -1, so the complementary solution is equal to c1 e power 0x plus c2 plus c3x into e power -1 is the repeated root. Now to find the particular solution for the non-homogeneous third order linear differential equation. For the particular solution, we write 1 over differential operator d cube plus 2d square plus d into right hand side function. In the right hand side function, we obtain two different form of functions. One is the exponential and other is the polynomial x square plus x. So e power x is the first case. How to find the particular solution? When in the right hand side there is the exponential function, then we find the particular solution for the exponential function. Just replace this d by this argument 2. So putting d is equal to 2, you see over here, this is the particular solution for e power 2x, 2 power 3, 2 into 2 power 2 plus 2 into e power 2x. Now the particular solution part for this polynomial, for the polynomial, take the lowest degree term. We take common the lowest degree term. D is the lowest degree term. Degree of this term is 3, degree of this term is 2, and degree of this term is 1. So this is the lowest degree term. So taking common d, we can write 1 plus 2d plus d square. Multiply this d again, we obtain this expression. 1 into d, d, and 2d into d, 2d square, and d into d square, we obtain d cube into the given polynomial x square plus x. Now after simplifications, we obtained in this part 1 over 18 e power 2x. Now the complementary solution for this part is complete. This is the particular part for the exponential case. Now the particular part for the polynomial is now remaining, so we are going to find the particular part in case of polynomial. 1 over d and 1 plus 2d plus d. 1 is the first term for the binomial expansion, and 2d plus d square is the second term. So we can write 1 plus x, this is actually represent the x, which is second term, and shift this expression to the denominator. We can write 1 plus into 2d plus d square power -1. So this is a binomial expansion. So for the binomial expansion, we write this 1 plus 2d plus d square in the form of 1 plus 2d plus d square. 1 is the first term, and 2d plus d is the second term. Now shift this expression to the denominator. To the numerator, we obtain 1 plus into 2d plus d whole power -1. This is the first term and this is the second term, binomial expansion into the given polynomial x square plus x. Now expand this term binomially. 1 plus nx, this is n, and 2d plus d square is represent the x term. So n power -1, so minus into plus minus 1 plus nx plus n into n minus 1 divided by 2 factorial. After expansions, n into n minus 1, n is the -1 into -1 minus 1 minus 2 in minus 1 plus 2 in plus 2 is cancelled with 2 factorial, and x square, this is actually the x term. So 2d plus d square whole square, and so on into the given polynomial. Now since in this polynomial we have largest degree 2, so we need only d and d square. We don't need d cube and d power 4 and the higher power of d. So we take just a square term, a square plus b square mean d power 4. We don't need d power 4 and we don't need the 2ab, because the 2ab term will obtain d power 3, and we don't need d cube and higher power. So we can take only the a square term, which is 4d square, and you see over here in the coming slide. 1 over 18 e power 2x is the particular part for the exponential, and plus 1 over d into 1 minus 2d minus d square plus 4d square. You see over here minus 2d minus d square plus 4d square into the given polynomial. Now d is the first derivative for this polynomial, d square is the second derivative for this polynomial, and after simplification minus d square plus 4d square means 3d square. So x square plus 1 multiplied with 1 we obtain x square plus x, and 2d multiplied with the polynomial, and similarly 3d square multiplied with the polynomial. So x square plus x is as it is, and d means the derivative of the x polynomial. The x square derivative is 2x, the x derivative is 1, and now the first order derivative is 2x plus 1, and again the derivative of this term will be 2, and the one derivative is 0, so 2 3 the 6, and now 2 to the 4 minus 4x and minus 2x, so x square x and minus 4x minus 3, and plus 6 minus 2 is plus 4, and now 1 over d mean integration. The integration of x square will be x cubed by 3, the integration of x is x square by 2, and the integration of 1, you see over here 1 integration is x. Now the integration of x square is x cubed by 3, the integration of x is x square by 2, and 4 is common, but we obtain 1, integration of 1 is x. So this is the complete particular solution. Now the general solution of the given differential equation is equal to complementary solution plus particular solution. The complementary solution is c1 e power 0x plus c2 plus c3x into e power minus 1x, and the particular solution you see over here 1 over 18 e power 2x plus x cubed by 3 minus 3x square by 2 plus 4x. So this is the complete solution. This is the complementary solution, c1 e power 0x plus c2 plus c3x into e power minus 1x, and this is the particular solution. So dear students, the conclusion of this lecture is how to find the particular solution when we obtain a polynomial in the given non-homogeneous linear differential equation. So this is, suppose this is a polynomial x square plus x, in this problem you see over here this is a polynomial. In case of polynomial, we can find the particular solution by using the binomial theorem. But first of all, make the binomial theorem in the differential operator. How to obtain a binomial theorem in the differential operator? Take the lowest degree term and consider one term will be the first term, and other term represent the term x, and then use this binomial formula 1 plus x power n, 1 plus nx multiplied n with this second term, 1 plus nx divided by 1 factorial plus n into n minus 1 x square divided by 2 factorial plus n into n minus 1 into n minus 2 x cube divided by 3 factorial, and expand this binomial theorem according to the degree of the polynomial. If we have a polynomial of degree 2, then expand this binomial theorem just to this third term, and if we have first degree polynomial, then expand this binomial theorem just for two terms, 1 plus nx by 1 factorial. And after expansion, we need only that power of the differential operator which lies in the given polynomial. According to the power of polynomial, keep these power of differential operator. Now this is the end of this segment. Thank you. Allah Hafiz.